Hey folks, so I did this video on Broyden's method, a 2D function here, and if I run this right now before I edit the code, it does this. It's this huge two-dimensional map here that's essentially trying to find this this solution to these two planes colliding with each other. And I had a YouTube user, Klaus Antonio, ask me a question and say like, hey, how do I convert this to 1D? Here's the function f of x equals this. And I thought it was an interesting question, so I figured I'd just do it. So what we're going to do is we're just going to convert everything to what's it called? To 1D. And he said that he was going across -1 to 1, so I'm going to do -2 to 2, which is fine. I don't need to do a mesh grid or anything like this. I don't even need to do any of this because it's all 1D, so I can just say f equals f of x. I guess y. And then I guess down here at the bottom, here's f of x. Yeah, there's the error function. So I guess what I need to do is I need to say, I need to grab this guy here, copy, and then throw this here. And say, I'm going to change this to y. And then, oh, okay, I see what's happening here. So x is still a, x is still a multi-dimensional variable. Shoot, I kind of need to start over. Oh, I guess I didn't catch that. So x is still a 2D variable, but instead of doing z1 and z2, we're just doing z1. Okay, so this is x1, x2, and then what? x1, x2 is mesh grid of x1, x2. And then so we just have what? We just have ZZ. We don't have ZZ1. We just ZZ is 0 times XX1. Okay, my bad. And then there's no out 1, it's just out. And so I can just do f of xij. Okay, so I don't need this. Okay. So if we pop down here to the function, here's f of x. So let's grab this again. Copy. Okay, so this is still good. I'm going to do out equals. I guess I don't need this. And I'm going to do dot times. No, I don't need to do. Yeah, I don't need to do dot times because I'm just going to give it a scalar function. Okay, so I think that will work. Okay, so that'll give us the mesh grid. I just want to plot mesh ZZ. Let's see, Newton's method. Let's see, so I guess let's just do this. Solve for x such that f of x equals 0. That's fine. So while error of x, so I guess this is our initial condition, 2, 2. Let's see if this function error is correct. So if we go to error, out is f of x. So my out error, there's only one out. So I guess I can just do f of x squared because now f of x is just a scalar. Okay, so that changes that. Alright, so we're going to say while error is greater than or equal to 10, so we say s is inverse j of x times f of x. But see now, f of x is a scalar, and so inverse of j of x is just divided by j of x, right? Because there's no... But see, x is a 2 by 1. So you actually want to do, yeah, I'm drawing a blank here. You want to do the gradient of, see, x next is x now minus f of x, which is a scalar, divided by f prime. Well, not necessarily. F prime is going to give you a gradient. right? But you can't invert f prime. F prime is a 2 by 2 since f of x is a 2 by 1. No. Okay, so hang on. So this is for 1D. F is a vector function now. So you have x next equals x now minus times this. So you have x is a 2 by 1, right? F prime is also a 2 by 1. So you can't make it a 2 by 2 because f is a 1 by 1, right? So if you have x equals x1, x2, f prime, the only thing you can do is df dx1, and then dx2. That's all you can do. So you're still going to get a gradient. So maybe I think you need a dot divide. Does that make sense? Yeah, you need a dot divide. So it's just f prime and it's dot divide. So f of x, this function here is a 1 by 1, and then this is a 2 by 1, and you want to dot divide it. So s is now a 2 by 1, and then you get that there. Okay. So let's throw a break in here. Let's see if this works. Let's find f prime. So there's out error. J numerical, not used, it's fine. Here's J. So I just want f prime, and I kind of want to move this up so I can see it. So here's f. Okay, so f prime, so it's df dx1 and then df dx2. So df dx1 is 2 times x of 1, or x1. And then the second term goes away, and then the derivative of this is what, 20 times x2? Okay, so I think that'll work. So let's give that a go. Okay, so let's not use a break, let's use a return. I got a NaN solution, that's no good. Okay, so does this ever hit 0? It hits 0 at 0, 0, oddly enough. Okay, so let's see what's going on here. So what's x? Oh, this is a function? Why did I do that? I don't want to make this a function. Okay, so let's try this again. There's an end statement at the very end. There's an end somewhere. All functions in a script must be closed with an... Oh, it's because there are functions within functions here. Okay, that's why. Okay, so I guess what I'm going to need to do is I'm going to need to print x, print f of x, print f prime of x, and then print s, and then the new x. Let's see what's going on here. So it looks like Newton's method is totally blowing up. And it's either because we need to add an alpha parameter here, or it's because my equation is wrong. So let's just throw an alpha parameter in here. Okay, it made it. So it was just an alpha parameter. It was ill-conditioned, and so the whole thing was blowing up. But yeah, there's Newton's solution. So we can get rid of all of those prints now. And so there's Newton's solution. I'd like to see display f of x. I'd like to see how close it got. Yeah, there's 10 to the minus 6. Oh, but I guess we need to do, what, error of x? Right, well, it's not f of x. Yeah, okay, so the error is minus 11. Okay, so let's see if the secant method is working now. How are we doing on time? 10 minutes? It's not too bad. Okay, so then same thing, reset x, and then, okay, so now we're doing f secant, and it's not inverse, it's f of x dot divide. And then basically what you need to do is you just need to do finite differencing. So we'll say function out equals f secant of x. x1 is x of 1. x2 is x of 2. And then out is, out is, let's do 0, 0 for now. And then out of 1 is f of x1 plus dx minus f of x1 minus dx all over 2 times dx. I'm doing central difference in here. And I guess I'll pick 1e minus 6. Seems reasonable enough. And remember, f is a scalar, right? So then out of 2 is basically just copy the same thing, except instead of perturbing x1, we'll perturb x2. Let's see, index exceeds matrix dimensions. F secant of x. Oh, I'm passing it a scalar. Whoops. You need to do x of 1 plus dx. X of 1. No. How do I want to do this? Because you still need to send f of x a scalar. You still need to send f of x. I guess I'm going to do it this way. This is kind of a hack, but so I'm going to send it a vector like this. See that? And then down here, I'm going to send it x1 and then perturb x2, and then send it x1 and perturb x2. Let's try that. Okay, that worked. And then at the bottom here, it looks like the secant solution blew up. Oh, it's because I didn't put the alpha parameter in there. So let's throw alpha times, and then let's throw alpha up here. Okay, secant solution display x, display f of x, display error of x, and then throw a return in here. Okay, cool. So there's the secant solution. So the Newton solution, the secant solution, they all pretty much converge. That's 1 times 10 to the minus 3 of these two numbers here. I guess I could plot it on this graph, but whatever. Okay, so now we're getting to Broyden's method here, which is what the what's his name? Klaus? It's what Klaus Antonio. It's Antonio. That sounds Italian, but it could be. I guess it could be German. Anyway, hello from the United States, if you're watching. So let's see. So we initialize x, and I guess we get rid of this return, and then we initialize b. Now the thing is we have to be careful with how this equation works, right? So s is inverse of b times f of x, and then x1 is x plus s. So we know that x1 is a 2 by 1 because x is a 2 by 1, which means s is a 2 by 1, right? So if s is a 2 by 1, it means that b is also a 2 by 1. Okay? So rather than making it identity like this, I think we just do 1, 1. And then I think we do the exact same thing we did before. We do f of x dot divide by b, like that, because that should work. Okay, and then here, y, this is a difference here. So y is a 1 by 1, right? Because f of x is a 1 by 1. And then here, this is still a 2 by 1. Okay, then recompute and update the approximation of b. Okay, so s is a 2 by 1. So if I do s transpose times s, so s transpose is a 1 by 2 times a 2 by 1 will give me a 1 by 1, which is fine. So that's a scalar. So that's exactly what I wanted. Okay, and then let's see if these matrix dimensions work out. So y is a 1 by 1, right? And I subtract b, which is a 2 by 1, times s. And what's s? S is also a 2 by 1. So that doesn't work out. So how did this work before? Before, y was a 2 by 1, and then b was a 2 by 2, and then s was a 2 by 1. But now b, so maybe b is just a, is it possible that b, no, because it needs 2 degrees of freedom, I think, still. I wish I knew what this formula was doing. Y minus b times s. See, what if I just do dot times and then just subtract y from it? But then I'm going to do a 1 by 1 minus. See, this is going to be a scalar. S transpose S is a scalar. And then b is a 2 by 1, and that's a 2 by 1. So this whole thing here needs to be a 2 by 1. So if we do y, then y is f of x1. So that, I mean, there's nothing I can do about that. So y is a 1 by 1 minus, let's see, a 2 by 1 times a 2 by 1, which isn't going to work. And then this whole thing, MATLAB is just going to subtract y from both. So this is basically a question mark. And then it's multiplied by S transpose, and S transpose is a 2 by 1, S is a 2 by 1, so that's a 1 by 2. And I need the result to be a, see, I need the result of that to be a 2 by 1, and so that's not even correct. So I wonder if I just need to do dot times everywhere. So if I do a dot times there, that's a 1 by 1 minus a 1 by 1 minus a 2 by 1 times a 2 by 1 dot-wise operator, dot times a 2 by 1. Unless I need to, unless b is a 1 by 1. That's the thing. Maybe b is a 1 by 1. Let's see if this works. I doubt it. I think I'm in an infinite while loop. Yeah, X blew up. Okay, so I guess we're in a position where I don't know what to do. I guess I don't understand Broyden's method enough. So let me go online on Google and see if I can figure something out, and then I'll come back. Okay, folks. So I found this website here, and this is kind of interesting. So it says BK is the Jacobian approximation of iteration k, right? So S is x k plus 1 minus xk. So that means S is definitely a 2 by 1. But what's interesting here is that B times S is F minus F. And this is a 1 by 1 minus a 1 by 1, which means B times S has to be a 1 by 1. So if S is a 2 by 1, it means B is actually a 1 by 2. So that completely changes things. So B is actually a 1 by 2. Now, the problem I have with this, though, is that when I compute S, and maybe I'm computing S incorrectly. See, S is the difference between two iterations. Maybe I'm calling S. No, I mean I think no, that's right. Yeah, S is the two different iterations. But basically, S is the difference between the iterations divided by B, and so if I want S to be a 2 by 1. I mean, maybe I just need to do dot divide by B transpose. And then that would give me this here. Y is definitely a 1 by 1. I reset X. This is definitely a scalar. And then this is a 1 by 1. This is a, so let's go back to the formula here. So it's Y minus B. So B times S should be fine. So because B is a 1 by 2. S is a 2 by 1. So that's a scalar. So that's a scalar minus a scalar. Dot times, let me get rid of the dot times and times it by S transpose. So that's a 2 by 1 converted to a 1 by 2 and then divided by a scalar. So that's right. Okay, so let's try that. Let's see. No, it still blows up. So I think so how do you get B0? Given an initial matrix B0, often a finite difference in approximation Jacobian. So that's the other thing, is maybe our initial guess of B is incorrect. So what if we just make B the F secant transpose? still blows up. Is it another alpha thing? Here we go. Let's do alpha. It's not blowing up. Let's make our alpha smaller. What was alpha before? 0.01. Let's try 0.001. I mean, those numbers are getting smaller. 2.1, 1.9. I mean, this might just be a very ill-conditioned problem. So the top number went down, and then it goes back up. Yeah, it's not. Oh, gosh. That blew up. Whoa, it came back. No, it blew up. Now it's in like some weird, crazy stable limit cycle. Let me research some more. I think something's wrong here with this S here. Give me one more second. Okay, folks, I checked another website, and basically this delta term is exactly what I had, and it turns out it actually works. I don't think I changed the code anything since then. I changed the error threshold, but yeah, I mean, if you look at the error, the solution is not that great, but that's because I let my error be really big. What's interesting though is if you compute num iters and you say num iters equals num iters plus 1, and then you go ahead and say display num iters, and then do the same thing here, num iters 0, num iters equals num iters plus 1, and then down here display num iters, and then here num iters equals 0, and num iters equals num iters plus 1, and then you display num iters. So we should see an integer after all of these, and what is interesting is that Newton's was 1500, Secant solution was 12,000, and Broyden's method was 354,000. And then if I do 0.1 for the error threshold, Broyden's method goes up to 500,000. If I keep going and try to get a better estimate, I mean, Broyden's solution, like I don't exactly know if it's just this specific problem, or if it's something wrong with my computation, but I don't know. It might be that scalar functions do not lend well to Broyden's method, and it might just be that, I mean, at this point, like Newton's method is way better. I mean, we could even do a tick and a talk, right? I think the whole point of Broyden's method is to save time, right? And if we're sitting here, tick, talk, and then tick, and then talk, right? So I mean, yeah, you're talking about Newton's method took way less than a second, and Broyden's took 2. Again, and it might just be because oh, whoops, I changed it in the wrong spot. No, I didn't. Did I change it in the wrong spot? Yeah, Newton's solution is still fine. But yeah, unless you make that alpha parameter small. So what's happening with Broyden's method I looked up is that you are approximating the Jacobian B. If you look in this spreadsheet, basically it's saying, here's Newton's method, yada, 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 the x minus Jacobian inverse. And then down here, it's saying like, hey, we don't want to evaluate j of x at every time iteration. It takes too much time. So, okay, whatever. So anyway, so then they use this like crazy update formula to update it, and this is faster than computing the Jacobian, and then apparently this speeds up time. But if you're trying to save time by not computing the Jacobian and approximating the Jacobian, then it's not working, right? Like this is the actual Jacobian, this is the secant method Jacobian, right, using the numerical method, and then here's Broyden's method's estimate. It's terrible. And again, maybe it's my formula here, and I mean, post in the comments and see if I have an error. But you know, let me open up file. Open. Here's Broyden's method. Here's the first one, right? So, you know, here's Broyden, Newton, secant, Broyden solution. I mean, here's the approximation of the Jacobian. Even in this one, it's pretty bad. I mean, 1, 2. Yeah, it doesn't estimate this bottom one at all. So I don't know, maybe other people have better luck. I mean, I'm not a numerical method guy. I mean, I just use computers to solve aerospace problems. So I'm not entirely, this is like outside my area of expertise. But I don't know, I guess my conclusion is just use Newton's method. I mean, that was way better. Anyway, Klaus, I hope you enjoyed this video, and I hope you learned something. I'm going to push this code so you can have it and use it. If you are doing this for a homework problem, make sure to cite me and give me credit. You know, plagiarism is a real thing. And yeah, good luck, and I hope you guys stay safe out there.